In this lesson we're going to look at the industrial electrolysis of brine. Now brine is the old-fashioned word for salt water. That's sodium chloride that's been dissolved in water. Okay, and the apparatus that's used is called a diaphragm cell here, and we'll talk about that in a minute, but the brine goes directly into this cell here, the brine water. And you'll see here we've got the positive and negative terminals of the battery. So this is the positive anode and this is the negative cathode. Now here we're performing the electrolysis of an aqueous salt solution. And in this case, that means that there are effectively 4 ions present. We have ions present from the ionization of the salt itself. So we have sodium chloride ionizes to produce sodium ions, we'll put AQ in solution, plus chlorine ions. But not only do we have the ionization of the salt, but also the ionization of water takes place. So you have 2 extra ions, H2O ionizes to produce the hydrogen ion and hydroxide ions. And we'll represent these ions like this. And let's introduce them into this brine solution. Okay, so we've got sodium ions, hydrogen ions, those are the cations, and then the anions, we've got the hydroxide anion and the chlorine and the chloride anion. So we need to apply the anode and cathode rules to decide which is going to be reduced at each electrode. So first of all, let's look at the cathode. And we remember that it is the ion of the element that is less reactive that will be reduced at the cathode. That's to say, if we look at the reactivity series, we've got sodium up here, it's way above hydrogen, so that means that it will be the hydrogen ion that is reduced at the cathode. So the hydrogen ion comes in and will gain an electron to produce a hydrogen atom. Let's just run that. So we have the cathode, hydrogen ion gains an electron, that means it's reduced and forms a hydrogen atom. Then the hydrogen atoms then combine to form a diatomic hydrogen molecule, so we need to balance this equation. We need to put a 2 there and a 2 here to balance the charges. So we're going to get hydrogen. This is the first product that's going to be liberated. We're going to get hydrogen gas produced at the cathode, and that's going to be collected and used for industrial purposes, which we will look at in a minute. Now at the anode, we remember that the rules are, if the aqueous solution is a solution of a halide salt, which is the case in this situation, then it will be the halogen gas that is produced at the anode. That's to say, the halide ion will be oxidized at the anode. The chloride ions will be attracted to the anode and they will lose an electron. Let's do that, Cl minus, and we represent it this way. We have the arrow, and that forms the chlorine atom, and we lose an electron. That electron will then go around the circuit and be given to the hydrogen at the other end. So we need to balance that again, because the chlorine, again, just like the hydrogen, the chlorine atoms join together to form a diatomic molecule. They don't exist as a single atom in nature, they form diatomic molecules, so we need to put a 2 there, which means we need to put a 2 there and balance the charges with the 2 there. Okay, so we're going to get, delivering at this end, we're going to get chlorine gas coming off. Cl2, and again that will then be collected for industrial purposes, which we will look at in a minute. Now, as a result of the reduction of the hydrogen ions at the cathode and of the oxidation of the chloride ions at the anode, that's to say the liberation of hydrogen and the liberation of chlorine, what's going to happen is the concentration of the sodium and the hydroxide ions are going to increase. That's to say, because we're effectively removing this ion and this ion from the solution, it stands to reason that the concentration of the sodium ions and the hydroxide ions is going to increase. In other words, we're going to get an increase in the concentration of sodium hydroxide in this part of the diaphragm cell. Now, the concentration occurs in this part of the cell for a reason. That's because this diaphragm, as I'll mention later on, blocks the hydroxide ions from moving into this part of the cell. So we can represent the increase in concentration of sodium hydroxide by changing the colour of this solution. And this can be used again also for industrial purposes. So we're going to remove the sodium hydroxide via this tap. Okay, so our electrolysis of brine is resulting in 3 useful products. We've got chlorine gas. Well, chlorine gas is used for disinfecting swimming pools, for example, and also particularly in the purification of water, cleaning water. Very good for killing bacteria, chlorine gas. Okay, so hydrogen is a very useful fuel. It releases a lot of energy when burnt in oxygen, and its only product is water, so it's a clean fuel. A lot of interest in using hydrogen as a fuel, but it's also used in the Haber process, which is an industrial process which produces ammonia, another very useful product, and also in the hydrogenation of oils to produce fats and margarine. Now finally, sodium hydroxide again is a very useful product. This is run off here at this tap, and this, as you probably already know, is an alkali and is used to produce soap, and also is used in the manufacture of bleach. In fact, this leads us now to the reason why this diaphragm is here, okay? And the diaphragm stops hydroxide ions passing through and coming in contact with chlorine. If this were to happen, then the chlorine would react with the sodium hydroxide and form bleach, which is not what we want in this situation. We want to produce just the chlorine gas. So if you remove the diaphragm, then what will happen is bleach will start to form in the solution as the sodium hydroxide reacts with chlorine being liberated from the anode. So the diaphragm stops that occurring.